David Smith here with one more Flip Classroom math video. 3 tips before we start. First, you can increase or decrease the playback speed if that helps you get through the video. Second, you can pause the video at any time to catch up with your notes. Third, you can turn on the captions or watch my words go by on the bottom of your screen. Today's lesson covers more of our work with the first derivative, minima, and maxima. So we're going to do that in the context of optimization. So a lot of situations you're trying to optimize something, volume, surface area, and so on. So a lot of our equations for geometry, the geometry of solids, comes into play here. So you're going to want to know where those are on your formula booklet, and then you're going to want to know how to use them. Okay, so what I've got here is a step-by-step set of instructions for how to attack one of these problems. Now obviously you can't bring this in on an IB test, but if you do this enough times and work it through, you should be able to follow these steps without this prompt. But for now, if you need it, just refer to your notes and follow these steps. Okay, let's go over them real quick. You need to determine the relevant formulas. These are the constraints. This could be the volume and the surface area formula, like for a cylinder. This could be a whole lot of different formulas. You need to figure those out. And then you need to take one of those formulas and solve for one variable. The idea is that if we do that, then we can insert the other side of that solution into the other formula and wind up with a formula that has only one variable. Then we can optimize. So determine optimizing formula, substitute to get one variable. So that's when you substitute the other side for the variable, take the derivative. And we take the derivative because we want to find, the derivative gives you the rate of change. So it could be the rate of change of volume, it could be the rate of change of surface area, or in a manufacturing problem, it could be the rate of change of profit. So we set the derivative equal to 0 and we solve it. So this finds the places where the rate of change is 0. So that's where the quantity that we're trying to maximize goes from increasing to decreasing or the other way. So we need to solve it. We'll get 1 or 2 x values from that. Then we perform the first derivative test. We need to find out where the function is increasing and decreasing. And that's where we use the sign diagram. Lastly, we solved, we maximized, we got a variable. We knew, say, that the volume is maximized with a certain radius of the cylinder. Then you need to find the remaining variables. If it's a cylinder problem, you're going to need to find the height. Or the problem might be asking you for something else, and you just need to read it carefully and make sure you answer all the questions. Okay, let's do a problem. So here we go. We have a semicircular water trough with a surface area of 10 square meters. And let's take a look at what that is, that water trough. Over here, here's my water trough. It's basically a cylinder cut in half longwise along the height. So just to know, a semicircle is a very precise term. It's a half of a circle. So if that were my circle, my semicircle is exactly half of it. So this semicircle has half the area of the circle, and it has half the circumference of the circle. So that tells you some very specific things about our water trough. Okay, so your first step, remember step 1, find the constraint formula. So first off, just write down the 2 formulas that apply in this situation. And it's right here. We have surface area here, and we want to maximize volume. Okay, so I didn't go over the prompt. Here is the prompt. Find the dimensions that maximize volume. Okay, so we know the surface area, but we want to construct this thing in such a way that it has the maximum volume. Okay, so constraint formula. Pause the video and see if you can come up with the 2 formulas that are important in this case. Okay, here are the 2 formulas that we're going to need. Straight up here is the volume formula for a cylinder, pi r squared h. That's the area of the base times the height. That gets you the volume of the cylinder. The surface area has 2 terms. 2 pi r squared gives you the area of the bases, so there's 2. And then 2 pi r h gives you the area of the outside, the lateral surface area of the cylinder. Now, we have to do something to this before we can start using it as an equation. So pause the video and figure that out. Okay, so I plugged in the number from my problem. I know my surface area is 10. Now notice how I took the 2's off of there. So I just have pi r squared and pi r h. Why did I do that? Think for a minute, why would I do just that? Okay, it's because this is for the whole surface area of the cylinder, but my semi-cylinder is exactly half. So I have to take a half of this and a half of that, which means the 2's go away, and this is my formula where I use my data here, and that's equal to the surface area. Now, we can't solve this one because it's one equation with two different variables. So we're on to the next step. Boom! Okay, the next step was solve for one variable. So I could solve for r or I could solve for h. I want to solve for h. Firstly, r is squared. I'm going to have to deal with that in some way. H is just in one place, and I could just isolate it alone. Second thing is that when I go in, insert that in here, I don't have to square it. I just put my h right there. So pause the video, solve this equation for h. Okay, let's see how you did. Here's my plug-in step, which is right from here. Just transferred it on down. So I'm needing to isolate pi r. I'm needing to isolate my h. So the first thing I do is I subtract this term over to the other side. I get 10 minus pi r squared. Then I divide through by pi r, and I have this expression equal to h. So let's move on to the third step. All right, I'm going to put steps 3 and 4 together because looking over my notes, I realized it really is just one step. We need our constraint formula, and we use substitution to get it. So volume is the thing we're trying to maximize. The constraints on volume are the variables in the formula. So before we go on, I want you to tell me why 1/2 showed up here. Pi r squared h is the formula for volume of a cylinder, but I put a half there. Why would I do that? Okay, if you remember from the graph, a semicircular cylinder has half of everything a cylinder has. So the volume formula that we're trying to figure out to find a constraint for so we can maximize volume has a 1/2 in front of all of that. Okay, so now you have everything you need. You might look up in your notes a little bit for finding the h substitution. I want you to pause the video and put the h in there and come right back. Okay, pretty much a straight up substitution. Here's what we got from the last board for the value of h in terms of r. So this is h, so we just plugged it in for h. Put it right there. Now here is my volume formula with just one variable, r. So ultimately where we're going to find the value of r that maximizes the volume. So calculus is coming. We're going to take a derivative. But before we do that, we need to put this function into a better form. I can't run the power rule on this at all. So pause the video and do your algebra here and turn that into a function that you can use. All right, let's do the steps. This is straight up algebra with a fraction and some canceling and a little bit of powers involved. So what I did is I just multiplied this term by that term. So we'll first handle the bottom part. This is 1/2, so that 2 is multiplied by the bottom. So I just have 2 pi r on the bottom. Then I'm going to take this term, pi r squared, and multiply it by 10. So I got 10 pi r squared. And then multiply it by pi r squared, I got pi r squared. So this is going to be pi squared r to the 4th. Now you could probably do some of that in your head and skip these steps. I like to be ultra super clear. Now I have things in here that I can cancel in both of those terms. So I'm happy. This is going to get less complicated. First, the 2 and the 10 cancel and we get a 5. And then the 2 and there's a 1 there cancel and we wind up with a 2 on the bottom. So now my pi r is going to cancel out the pi and the squared on the r. So that's gone, and I have 5r is what's left of this term. Okay, and it's not under a fraction because we got a 5 divided by the 2. Okay, now I'm going to do 2 pi r on that term. We handled the 2 already. We put this term over to the pi here is going to cancel one of the pi's, and the r is going to cancel one of the r's. So we wind up with 5r minus pi r cubed over 2. So that's my formula. That's my volume formula. Now I did one more step. I put it into a derivative-friendly form, which really just meant I took the over 2 and I made it 1/2 times pi r cubed. So now we have our constraint formula. This is volume as a function of r. So now what we need to do is find out the value of r that maximizes the volume. And we will do a little bit of differential calculus to do that. At last, we get to do a calculus step. Find the derivative of our function, which is change in volume over the change in radius, dv dr. And so what I did is I put my volume function here. That's what we did. And instead of pausing the video and make you do it, I went ahead and did that for you. 5r becomes 5, and then minus 1/2 r cubed becomes 3/2 r squared. Now, I would recommend that you pause the video and do the steps to get from here to here, because that's a good practice of your power rule on an expression that's a little bit complex. Okay, so now we are at the cool spot. Set equal to 0 and solve. I want to pause for a second. Why do we set the derivative equal to 0 and solve? What's the reason for that in terms of what we're trying to do with our problem? Pause the video, just think a little bit and come back. Okay, so remember, the derivative gives you the rate of change of a function. So we want where the rate of change is 0. That's either a maximum or a minimum. That's a turning point on the graph of the function. So when we set it equal to 0, we can solve for the r that gives us that turning point, and then we can find out whether it's a minimum or a maximum. So go ahead and do that. Set this equal to 0 and solve. All right, let's see how you did. So set it equal to 0, just brought it down, put 0 in here for the derivative function, and then I moved things around. I moved this term over to that side to make it positive, and that's 5, and then I divided through by 3 over 2 pi. That got me r squared equals 10 over 3 pi. There's a little thinking there with fractions and so on, but you should pause the video if you're not sure how it got from there to there. And then finally, to get r alone, I just take the square root of both sides, and I have 10 over 3 pi square root. Now I pull out my calculator, and this gives me 1.03. Now let's pause. What does that mean? What does that value tell you in terms of our entire problem? Pause the video, think real hard, come back. Okay, so this is the radius that will serve to maximize the volume. Okay, so we've been going gangbusters, all these boards of algebra to get to this point. So now we know that a radius of 1.03 meters, this is meters, don't forget your units, that will give us the maximum volume for our cylinder. Okay, we're at the 7th step, perform the first derivative test. This will help us determine whether it's a minimum or a maximum, because we do need it to be a maximum. Now, in the last board, I stated that that was the R that maximizes volume. How did I know that? Check this out. Here's our function. This is our derivative function. This is where we maximize volume. Notice how it's a quadratic, and the quadratic term has a negative. So that means that this graph goes like that, and that means that this is a max. So I know from that we have a maximum. However, you might be asked to show that it's a maximum using the first derivative test. So go ahead, pause the video, set up your sign diagram. Okay, here is my point, max or min. We haven't showed that with this yet. So pick 2 easy points on either side. So 2 is a nice one for the right side, and 1 is a nice one for the left side. So go ahead, pause the video, and use these values and the derivative equation to figure out whether the function is increasing or decreasing for both those intervals. All right, here we go. Plugging 1 into the function. I can stop right there. This is less than that, so I know the answer to this one is going to be positive. So I know that the function is increasing on this side, on the left side of 1.03. Then I come in here and I plug 2 into my derivative function, and I wind up with an answer that's on this side. It's just going to be twice what it is here. I can just do that in my head. So this is going to be 9.42. Subtract from 5, you're going to get a negative number. Didn't bother to do that because I didn't need to. And so what you get then is on your sign diagram, you have a plus here for increasing and a minus there for decreasing. So if I could sketch this rough outline of the function, increasing, decreasing. So this right here is indeed a max. So there you go. And that's how we maximize the volume of our water trough. Now that you've watched the video, take a moment to jot down any remaining questions so you can bring them to our next class. Remember, you can also come back to this video again and watch it for deeper understanding. If you liked or enjoyed the video, please click like or subscribe down below.